Hello everyone, my name is Bodin Chinthanet, a specially appointed assistant professor at Software Engineering Lab, Nara Institute of Science and Technology, Japan. Today, I am happy to present our work Lags in the Release, Adoption, and Propagation of NPM Vulnerability Fixes. This work is initially accepted in the Journal of Empirical Software Engineering. So first, I would like to give you a definition of the third-party libraries. In this work, a third-party library is a software package that available for software developers to reuse its functionality in their software project. Within software package ecosystem, each libraries can be depend on each other and form as a network of packages. Nowadays, third-party library usage becomes an important part of the software ecosystem, as a lot of developers use libraries in their daily work. As you can see here, there's a lot of popular package managers that provide libraries from different languages for developers at the fingertips. This is supported by the report from GitHub that more than 65% of active repository relies on open source package. While using a third-party library gives a lot of benefit to developers, however, there are also a risk that can pose to clients. One of the risks is from security vulnerabilities, which is a growing concern for developers. As reported by Sneak.io, more than 70% of websites run at least one known vulnerability. The example of vulnerability in the third-party library is the recent incident with Log4Shell vulnerability, which allows attackers to access the executing environment remotely. This vulnerability affects a wide range of software and services such as AWS, Docker, or Minecraft servers. In order to mitigate the risk of vulnerability, developers are recommended to update their dependencies. The vulnerability in third-party libraries is not only affect the direct clients, but it also can cascade transitively across the ecosystem. For example, in these figures, if there is one library that has a vulnerability, it means that the direct client is affected by the vulnerability. Moreover, there are three more downstream clients also affected by this vulnerability as well. Currently, the vulnerability issues are in the focus from different sections. For example, the academia focus on the impact of vulnerability and try to use a novel technique to mitigate a risk. The industry focus on creating the practical solution such as a vulnerability detection tool, and the government focus on implementing the framework for secure software development. As shown in the previous studies, the vulnerability issue is focused from several points of view, but not on the vulnerability fixes, especially with the downstream clients. For example, several works show that the impact of vulnerability to the ecosystem is big, even though the beginning is from a single vulnerability. There is also a work show that developers have a slow reaction to the vulnerability update, which results as a technical lack of package dependencies. Hence, there is a gap related to the analysis of vulnerability fixes in downstream clients not only a direct client. So this study is an empirical analysis that focuses on identifying and characterizing lags in the release, adoption, and propagation of vulnerability fixes. This study used libraries and vulnerabilities within NPM ecosystem, which is considered as one of the biggest package ecosystem in the world. Here, I will use the example of vulnerability fixing process to visualize our analysis from libraries to downstream clients. First, the developer A is maintaining a library called package A, which has only one release. As the time goes by, that developer A can release a new patch to improve their package. Developer A also allows to release a new development branch to add new functionalities of the package. In this case, they release a new version called version 1.1.0. Things look smoothly for developer A until some developers found that there is a vulnerability in package A. In this case, package A in version 1.1.0 and older are marked as a vulnerable release. After the reporter reached out to developer A, they have to work on fixing a vulnerability. In this case, developer A takes some time to fix and make a new commit called fixing commit, and later release it as a fixing release, which is a version 1.1.1. Here we define a term called package size fixing release, which refers to how a version number is bumped from the vulnerable one to the fixed one. Developer can bump either major, minor, or patch, which based on the semantic versioning. From this example, the patch version is bumped. Here, we suspect that there is a potential lag in the fixing process, so we are set to manually investigate it at the commit level. And results show that around 64% of the vulnerability fixes are a patch landing. We also found that the fixing release usually bundle with unrelated commits. In detail, only 14% of all commits are actually a fixing commits, and they have only 10 lines of code by median. Back to the example, after developer A release a fixing release, they maintain the package in multiple version branches at the same time. As you can see here, there is a version branch 1.0, 1.1, and 2.0, and version 2.0.0 is the latest one. Then let's move to the direct client of package A. Here, client B in version 2.0.0 depends on package A in version 1.0.1, which means that client B is affected by the vulnerability of package A. So sometime later, after the fixing release of package A, client B update their dependency and use package A in version 1.1.2 instead, and release a new version called 2.0.1. As we can see here, client B have to update package A by bumping a minor version, as it did not follow the update of package A until the fixing release is out. Here we call the version change of package A in client B as a client-side fixing release. Here we suspect that there is a potential lag in the fixing adoption of client B. So we investigate the differences of package-side fixing release and client-side fixing release. The results show that 36% of patches from packages are adopted as a minor landing by clients. This means that clients keep outdated dependencies, so they have to spend more migration effort due to the potential risk from backward incompatible changes. And finally, in the case of downstream clients, they cannot adopt the fix from a libraries directly and are forced to wait for the upstream to update first. In this example, client C in version 0.0.2 depends on client B in version 2.0.0, which is affected by the vulnerability from package A. After that, client C released the new version that updates client B to version 2.0.1. As we can see here, client C cannot adopt the fix from package A directly and have to wait for client B to adopt the fix first. So there is a lag before client B adopt the fix. Then there is also a lag before client C is able to adopt the new fix from client B. In this case, we suspect that there are some factors that might influence these lags. So we investigate those factors on the fix propagation to downstream clients. In this study, we investigate two propagation influencing factors, which including vulnerability severity, which has 3 levels: high, medium, and low severity. Here we hypothesize that vulnerability with high severity should have less lags compared to the others, as it poses more threat to the ecosystem. So developers should quickly respond to this vulnerability. The another factor is lineage freshness, which refers to the branch of package side fixing release. Here we have the latest lineage, which means the fixing release is on the latest development branch, presented as blue dot and lines in the figures. And we have the supported lineage, which means the fixing release is on the other branch than the latest one, as you can see in the brown dot and lines in the figures. The result of the investigation show that linear freshness and severity influence lags. In more detail, the fixing release with latest lineage and medium severity suffer the most lags compared to the other combination of factors. Here is the lessons learned from our empirical study. First, the release cycle matter. There is a need for strategies to make the efficient updates, as our manual investigation found that there is unnecessary update bundled with the actual vulnerability fix. So there is a potential that we can improve the release cycle to reduce a lag. Second, Migration costs effort. If developers keep the stale libraries, it might increase the chance that there is a backward incompatible change. So we suggest that developers should frequently update the libraries to reduce the lags and their migration effort. And the third, awareness of fixes is important to allow quicker planning of update. Even though downstream clients cannot directly adopt the fix from the library, however, they could prepare themselves so the lag from migrating the upstream packages is minimum. That's all from my presentation. If you have any question, please feel free to contact me in this method. And if you are interested in our work, please check out our replication artifacts and the full version of the paper by this QR code. Thank you for your listening.